Thank you so much. So my name's Alexa. I'm a PhD student at Concordia, and this is a talk, but also a paper that we hope to get out soon that I wrote with some colleagues from Germany and my supervisor, Dr. Ben Eppinger. So first, just to make sure we're all on the same page, I'm going to be talking about two main decision-making strategies today, model-based and model-free decision-making, and how they change during healthy aging. So these two decision-making strategies are defined as follows. Model-based decision-making involves forward planning and is therefore effortful, but very flexible. And a very easy example to remember what this is kind of like leaving work and deciding which route to take to go home. And in the process of doing so, considering which routes have more or less traffic to try to get home as quickly as possible. In contrast, model-free decision-making involves no forward planning, is a simple association between action and outcome, and therefore is not as flexible, but definitely less effortful. And an example of this here would be deciding not to take the freeway based on the time it is. When we look at these decision-making strategies, there's a lot of literature that shows that these strategies change from young adulthood to older adulthood. In younger adults, we typically see a combination of model-free and model-based decision-making, but in older adults, they seem to primarily rely on model-free decision-making. And the idea here is this is due to the partly due to the functional decline of the orbital frontal cortex, which helps older adults or everyone represent a model of the decision-making environment. So kind of representing this map in mind with the likely delays due to traffic before deciding what you should do. So jumping right into the current project, our goal was therefore first to determine if reducing the demands on representing that mental model of the task environment would lead older adults to engage in more model-based decision-making. And second, to examine the neural dynamics underlying these deficits in model-based decision-making we see in older adults. To answer these questions, we administered a two-stage Markov decision-making task, which looks something like this on the left, to 26 younger adults and 25 older adults. How this task works is as follows. On each trial, participants will make two different choices. They will first choose between here what is illustrated as a downward flying plane and an upward flying plane. Following this choice, they transition probabilistically to two different planets here illustrated as these blue background and brown background. I'll come back to these transition probabilities in 1 minute. But once you arrive at this planet, two different aliens appear, and you must make a second stage choice between these two aliens. And once you've made that choice, then you finally either get the feedback of having obtained a small monetary reward on that trial or none at all. Now, back to our transition probabilities. In the cover story, participants are presented with, they're explained that these planes transition most of the time to different planets, whereby the downward flying plane would transition most of the time to the blue planet, but some of the time gets confused and ends up at the brown planet. And the same or the opposite is true for the upward flying plane, whereby it would transition most of the time to the brown, but sometimes to the blue planet. What we did here is manipulated this into two different conditions, where one condition, you can see here the 60-40, so the bottom row has a smaller difference between what we call a common and a rare transition, whereas our easier condition has a greater difference here, being 80% common transition and 20% rare transition. And what this task allows us to examine is the contribution of model-based and model-free decision-making in the participants. By looking at the first stage choice. So how this is done is if I were doing the task and I perhaps choose a downward flying plane on a given trial, and it just so happens that I get a rare transition on that trial, ending up at the brown planet instead of the blue planet. Now, if I'm using once I get to the brown planet, I would then maybe choose the alien that looks like Mickey Mouse, and then finally get a small monetary reward. If I'm engaging in a model-free strategy, I would create an association between the first stage action, so this choosing of the downward flying plane, and the small monetary reward I've obtained, and therefore I'm likely to repeat the first stage choice I did on the last trial, so choosing the downward flying plane once again. However, if I'm engaging in a mostly model-based strategy, I might actually integrate what I've learned over the course of the task about these transitions and realize that if I want to end up at the brown planet once again, I'm better to switch my first stage choice and choose the upward flying plane instead, as it is more likely to end up back to the same planet regardless of condition. The last point to notice here is that these rewards, the probabilities varied using a Gaussian random walk, which meant that once you learn the alien that gives you the monetary reward, it wasn't going to remain the same one entirely over the course of the task. You had to keep updating which alien was the one to give the monetary reward and get there accordingly. Now, beyond looking at this behaviorally, we examined EEG, so electrophysiological data here was recorded, and we focused on two main time points. So first, we looked at the P300 component, which here is elicited after the two aliens appear on their respective background. And this is hypothesized to relate to participants' prediction error regarding the state they should end up at following the first stage choice. So following the choice of the plane, where you should end up at in terms of planet and also aliens. We also examined the FRN, which stands for feedback-related negativity, and this is hypothesized to relate to participants' reward prediction error. So do you expect to get a reward following your second stage choice or not? We also ran a computational model, but given the time I have for this talk, I'm not going to go over that, but feel free to ask any questions you have about that after. Before we go into the electrophysiological results, behaviorally, we found that both age groups did demonstrate more model-based behavior in the 80-20 condition as compared to the 60-40, showing that our manipulation did work, and the behavioral level showing that they were able to engage likely in more of this strategy, hopefully because of the reduction in the effort required to create a map in that condition. Jumping right into our EEG results. So for those of you who are not familiar with looking at these types of plots, notice here that negative is upwards, therefore P300, which is typically a positivity around 300 milliseconds, is indeed this downward waveform we're seeing here. What you're looking at here first, just in the younger adults, is both conditions in both types of trials. So we're looking at the common trials in the solid lines and the rare trials in the dotted lines. And then our easier condition in the red and harder condition, so 60-40 in the blue. And what you'll notice here is that our common trials led to a greater positivity than our rare trials. And there's also a greater separation or distance between our common and rare trials in the easier conditions or 80-20 condition, as opposed to the 60-40. Now shifting over to the older adults, unfortunately, there was no effects here. So the take-home message from these two plots is that the P300 seems to co-vary with the degree to which younger adults update their cognitive map of the task, while older adults may have deficits updating the internal model of the task. The FRN, so now looking at the feedback-related negativity, we have a beautiful FRN component here in the younger adults following a non-reward feedback at the outcome phase of the task. And in the older adults, although this response is blunted, it remains significant. Therefore, here the take home would be that both age groups were able to integrate the outcome information. Beyond that, we also ran single trial EEG regression analysis. And the beauty of these regressions is it allows you to examine what is contributing to the components we just examined. So we focused on the same two components, but here examined the hypothesis that these different prediction errors would explain variance in the signal we're seeing. So first we looked at the second stage stimuli, looking at how much variance does the value prediction error at the second stage explain in the P300 component. So there's a lot happening here, but we're looking at the younger adults across the top, older adults in the bottom, and then the harder condition on the left, easier condition on the right for both groups. And the main idea here, without going into the details of it, is that we're seeing that the older adults' value prediction error explained more variance in the P300 waveform in the easier conditions, so in this 80-20 condition, as compared to the 60-40. In the older adults, unfortunately, the value prediction error did not explain much variance in either condition. So the take-home message here would simply be that older adults had difficulties representing the task structure, and as a consequence, were unable to predict the value of the upcoming states. So here we're going above and beyond what we were able to conclude with just the ERP components and understanding what is it that can explain what we're seeing in these components in either age group and why are we maybe not seeing it in the older adults. Next, looking at the FRN once again, but here adding as a regressor the reward prediction errors. So participants' prediction regarding the outcome they expect to get following their second stage choice. What we found here, although the statistics are not present, just for simplicity, in the younger adults across both conditions, we found a significant contribution, or the reward prediction error rather, explains significant variance in the FRN in both conditions, and the older adults as well. Interesting here, just to go one step further here, when we talk about reward prediction errors, we can examine signed or unsigned prediction errors. And this is just about keeping the positive or negative sign before that numerical value that represents participants' prediction error on a trial-by-trial level, whereby the signed reward prediction errors typically reflect participants' prediction regarding feedback being worse, which would be a negative reward prediction error, or better, which would be positive than they originally predicted. Or we can also look at unsigned prediction errors, which reflects participants' prediction regarding if they will obtain a positive or negative feedback. So I ran analyses with both of these prediction errors, and the interesting part is that we found that there was that the signed reward prediction error explained significant variance in the FRN, but the unsigned prediction error did not. So it really seems to be about feedback being better or worse than expected than the specific outcome they expected to get. So putting this all together as a conclusion, behavioral results did show that the 80-20 condition led to a greater contribution of model-based decision-making for both younger and older adults. Our EEG results show that the P300 co-varies with the degree to which participants update their cognitive state space of the task, and this was due to that single trial analysis regression, which included the state value prediction error. And then finally, the FRN reflects feedback processing, but rather than reflecting participants' specific prediction regarding if they would get a reward or not on that trial, it reflected their expectation regarding the outcome being better or worse than expected. So altogether, this is how we're coming to the conclusion that older adults seem to have a deficit in representing the state spaces necessary to engage in model-based learning. And just thank you to my supervisor, other collaborators from Germany. I have my email address here if you'd like to ask me any questions above and beyond the talk today. And then thank you to our funding agencies.
Thank you, Alexa. Are there any questions?